Alright, what's going on everybody? In this video, we're going to be talking about the limit definition of a derivative. Now I know that's probably like the first time that you ever heard the word derivative, but you're going to hear it for a lot more in the rest of the time that you're in calculus, right? So I really want to, in this video, establish what a derivative is, and then we'll do some limit definition stuff, right? So I'm going to start in this video by talking about instantaneous slope. We'll talk about kind of where that whole derivative piece comes in, all right? And then we will get into kind of deriving the limit definition of a derivative, like what that thing is, where it comes from, and all that. Okay, then I'm going to get into some derivative notation, some nomenclature, meaning like how we name things like that. Like I'll talk about like how we say that we're taking a derivative and different things like that. Like, just how we name everything. Notation is really key, all that stuff. Then we'll talk about doing limit definition of a derivative when we're trying to take a derivative of polynomials. We'll talk about it when we're trying to take derivatives of radicals, and then when we're trying to take derivatives of fractions. Okay, these are the three main cases that you'll see, and they all have different ways that you go about solving them, but really it ends up boiling down to pretty much just three main cases that you'll be asked on a homework or a test. Okay? And we'll also then talk about second derivatives. This is when you take a derivative not once, but twice. Okay, so it's going to be the same process like we're going to learn in these three sections, but you're going to do it once more. Okay, and so we'll talk about that, and then we will do some review at the end to make sure that you've got it all. Now, before I get into this video, I quickly wanted to mention my full Calculus 1 course, which I have listed in the description down below. Now, in this course, I give you a bunch more practice problems to go over, and I give you that in a form of a worksheet, but I also have a full video where I go over all those practice problems, right? It's great to have an extra video where you have more practice problems that you can do, because it really helps with retaining information. If you just watch this video and that's all you do, you might not retain everything, but if you have an extra video, it's going to be a lot easier to retain all that information. So if you're interested in that course, definitely check out that link in the description down below. Now let's get into this video. Now we'll start in this video by talking about instantaneous slope, right? And here, the first example I'm going to give you here is what's the slope of the line y equals 2x plus 3? Okay, it's not a trick question, right? If we think about the form of a line, right, the y equals mx plus b form, right? M is the slope, and what's the value of m here? Well, it's 2. Okay, so the slope of this line, right, the slope of this line is 2. Okay, now slope is really important, okay, and it's going to be even more important in calculus. Okay, slope, I'll leave this 2 down here for a second, it's rise over run. Right? It's how fast your curve is changing. It's how fast your graph is changing, right? And so, we graph something like 2x plus 3. It's going to look something like this. Okay? That's what your curve is going to look like. Okay? And there's actually some like physical meaning behind this. We're not just dealing with some random letters on a screen, right? There's also, you could think about this axis as being position, I'll call that x, and then this axis is being time. And so we get a position time graph. It's a graph that tells you where you are and at what time. Okay? And if you think about what slope is here, right, if this is our curve, if this is how we're moving through space, okay, well, what's the slope here? Well, the slope is, again, rise over run. And we know that in this case, right, in this graph, right, our slope is 2. But what's the units on that, right? Well, position is measured in meters, right? And time is measured in seconds. And so, well, rise, right? That's going to be, we're going to go 2 meters up for every second that we go over, right? Because, it's all over 1, right? And so that's our run, right? For every second that we go over, for every one of these pieces, we're going 2 up. We're going 2 meters up. And so and we can kind of get rid of the 1 here because it's just, it's kind of, redundant, right? And so we see that our slope is 2 meters per second, right? 2 meters per second, that is a speed, right? That's a velocity. Okay, so that's really interesting, right? The slope of a position time graph is how fast you're going, right? It's telling you how your position is changing in time. How your position changes in time is how fast you're going, right? And that should kind of make sense. So that's why slope is so important. Now it's really nice to, find the slope in an example like we have right here, but it might not be if we're talking about something like y equals x squared, right? That's not a line anymore. And we're only used to finding the slope of a line. Now, what if we have something like y equals x squared? And I'll just draw this in the first quadrant. Okay? For a graph like this, y equals x squared, right? If we're trying to find the slope at x equals 2, well, what does that mean, right? Well, again, the slope is just the rise over run, right? It's how fast the curve is changing in height versus how fast it's changing in the long direction, right? The x direction, okay? That's what rise over run is. And so that's still going to be applicable for any graph that's not straight, okay? And so when we talk about graphs that are not just like straight, like a line, we call that the instantaneous slope. Okay, because that slope's going to change. It's not going to be the same here, right? It's not changing as fast here as it is here, right? At this point, we're pretty much going straight up, right? But at this point, we're kind of going out this way, right? And you can kind of see that, right? And so this line right here at x equals 2, right? This thing is called a tangent line. And the instantaneous slope, right, of this y equals x squared graph at x equals 2 is really just, the slope of this line, right? Because this line represents how fast this curve is changing at this point, at x equals 2, okay? And so that's what we're really talking about here. But, it's not going to be so straightforward. It's not like we just plug in 2 for x here, right? And so, what we're going to have to do here, we need to create a slope function. Okay, we want a function that is going to tell us what the slope is of this graph at every x value, at every point. Right? We want that. And what that's called the derivative. Right, that's what the derivative is. So that's the derivative of y equals x squared, is a slope function. And that's what a slope function does. It gives you the slope of this graph at every x value. Okay? And so here's the thing though. How do we actually find this slope function? Well, what we're going to have to do is we're going to have to extract it from the y equals x squared graph, right? That's the graph that we have. And so what we need to do is use y equals x squared and extract the information about slope, so I'll call that slope info, from y equals x squared. Okay? And so we're going to do that, by taking a derivative. And we're going to do that with the limit definition of a derivative, which I'll talk about right now. Okay? And so, to figure out how to find our slope function, what we're going to have to do is we're going to make a couple modifications to the slope formula that we already have, right? The slope formula that we have, right? The slope is equal to the rise over run. It's the rate of change. Right? And we also know that as, we write that as y2 minus y1 over x2 minus x1. Okay? Now, if you want to write that a little more like with the f of x notation, right? Because we're used to seeing y as f of x now, right? We could rewrite this as f of x2 minus f of x1 over x2 minus x1, right? Where the y2 is just f of x2 and y1 is just f of x1. Okay? And so that's just going to help us to see what I'm about to write in a second here. Okay? And so now I'm going to define 2 points, okay? I'm going to define what x1, y1 is, and I'm going to define what x2, y2 is. x1, y1 is just going to be a random point, right? X, and then the y coordinate is going to be f of x, right? It's going to be what happens when I put this x into the function, right? And that's generally, like, that should make sense, right? Y, you know, that whatever goes here, right, is going to be what happens when we plug x into our function. When we plug, like, you know, let's say 2 into this, when we plug 3 into this, it'll be the y coordinate at 2 or 3. Like, that's the idea. Hopefully I'm not confusing you with all this notation, and I know it's a lot. Okay, so this is just some point on a graph, and I'm going to show you that graphically in a second. I'll show you like a picture, right? But really I'm saying, okay, well, we have some point here, it's at x, right? Some x value, and then some y value, which I'll call f of x. Okay? And what I'm going to do now is I'm just going to move a little bit over, right? I'm just going to see where this graph is going, and so I need another point, right? Just like we do when we're talking about regular slope of a line. And so I'm going to move over by h, okay? You know, that could be like 1 or 2 or 3, right? You know, that's just some number, and we're moving over a little bit. And so the, you know, respective y value would be what happens when I plug x plus h into the function. Okay, that's it. And so how you write that with coordinates would be, well, x plus h is the x part, and f of x plus h would be the y part. And I promise this is going somewhere. We're almost done here. Now what we're going to do is we're going to plug these points into the slope formula from before, right? We're going to plug it in. And when we do that, right, what is our 2 y points? Well, they are f of x plus h and f of x. And so our slope is going to equal f of x plus h, right? That's our y2. And then our y1 is f of x. Then in our denominator, right, we have x2 minus x1, which x2 is x plus h, and x1 is x. Okay? And you can see here that the x's cancel off, right? They subtract out. And so we get that our slope is f of x plus h minus f of x all over h. Okay, this is a really clean way to write it. This is going to be the slope of any curve, right? It doesn't have to be a line. It could be a curve. And so that's a really nice way to write it, okay? It's hopefully, you know, you get the idea, right? It's just we're talking about the slope between 2 points. Okay? Now, here's the catch with what we're doing, right? I know it's a lot of notation. You might not get where it's going yet, right? So you're going to want to probably review this after I talk about it. But we can't just pick 2 random points. Like, we can't just pick some random x and the x plus h. Here's why. Because here's the point at x. Here's going to be the point at x plus h. Would you say that this line represents the slope at this x? No, right? At this point, we're going this way, right? We're not going up this way, right? And so it's very off from what you would expect, right? We're going this way. So, you know, what we're going to do, let's start just getting these points a little bit closer. Let's move it a little bit closer here. We'll try this. Okay. Now we're at this, right? We're getting a little bit closer, right? We're kind of close, right? We're a lot closer than what we were right here. And so we'll move it closer again. We'll go x and we'll go x plus h. Okay, now we got 2 points. We link them up like this. I'd say that's a pretty darn good estimate, right? And if we go really close, right, we go like right next to each other, it's pretty much exact, right? I think you'd say that that's pretty much exactly where we're going, right? And so the idea is that as we shrink the distance between x and x plus h, our approximation of what the slope is gets even better. Okay? It gets better and better and better until it's pretty much exactly the slope, right? And so think about what this means here. That h is how far to the right we are of x. So we want that distance between x and x plus h to go to 0. And so h has to go to 0. Okay? Now, I did mention before, and again, I will rephrase what I just said on the camera because it's kind of hard to think about math when I'm just looking at you face to face, but I did want to get your attention for that. But yeah, you can see that as these points are getting closer and closer, we're getting a more accurate estimate of our slope. And the slope of the tangent line at that point is our instantaneous slope. We've talked about that before. Now to form this line, right, the distance between our 2 points needs to go to 0. And how do we do that? Well, we make a limit as h approaches 0, right? If h is 0, think about it. If h is 0, then we just have x, right? It'd be x plus 0, and that's x, right? And so we don't want h to be 0. We want it to travel to 0. We want it to approach 0 because we want to get these points so close to each other that our slope approximation is exact. All right? So that's how we get the limit definition of a derivative. As you can see, this is the slope that we just found out, right? That's the slope function. But the only catch here is that we want h to go to 0. And so how do we do that? We use a limit. And that's how we get the limit definition of a derivative. Now we call this f prime of x, okay? And that's the other new thing in this notation. That's our notation for the slope function. It's our notation for the derivative, which is right there, okay? So if you get that, right, if that makes sense to you, that's how we form the limit definition of a derivative, then all we really need to do now is just start solving problems, right? After we go over a little bit of notation, okay? So that slope function, right, as I said, is called the derivative, okay? And this derivative, right, what its job is to give you the slope of a graph at any x value, right? So, okay, the slope here is 2, the slope here is 3, the slope here is 4. Something like that, okay? That's what the derivative does. Now, the process of finding the slope function, what you're going to see here, it's called taking the derivative. Okay, that's kind of the verb that we use. We say, oh, I'm just going to take a derivative, right? And so that's the idea, right? And remember, we call that slope function the derivative. The notation that we use here, okay, we can label our derivative in 3 separate ways. Okay, we can call it f prime of x, that's the notation that I used before. We can call it y prime, okay? And instead of like saying y equals 2x, we'll be like, oh, well, the slope of that, y prime, is going to equal, well, the slope of 2x, right? The slope of the line 2x is 2, right? Or we could say that for dy dx, right? We could say instead of y prime, we'll say dy dx. Oops. Okay, and there is some more behind this notation because it just seems to kind of come out of nowhere with like d's and stuff. And so I want to explain that a little bit more. And so that's why down here I have that this dy dx has some meaning behind it that we should unpack, okay? If we have y equals 2x and we want to find the function that gives us the slope at every x value, right? That's called the derivative. We show that we want to do this by using the derivative operator, okay? And the operator, right, I'll talk about that in just a second here. But basically what it is, it just tells us that we want to do something, right? And so what we do is we put a d over dx on both sides. Okay, this tells us, hey, it's time to take a derivative. Now that's something that we don't know how to do yet, okay? But at least I want to get the notation out of the way so that when we start taking these derivatives, you know how to at least like show that we are doing it. Okay, on the right hand side here, or the left hand side, you can think of it as multiplying the y onto the d, right? And so you get dy dx. And on the right hand side here, right, that's what we don't know how to do yet. We don't know how to take the derivative of 2x. Okay, but that's all the d over dx is doing. It's just saying, hey, we got to take a derivative here. Okay, we'll figure out how to do that in a second. The dy over dx is the derivative, right? It's the exact notation that I was talking about here, right? It's something like y prime or f prime of x. Okay. Now, here's more on that operator thing that I was talking about. That word might confuse you a little bit. It confused me when I was first learning this. Now, taking a derivative is a operation, right? Just like addition, subtraction, multiplication, or whatever, right? You're still you're doing something, right? And examples of operators, right, are a plus sign, a minus sign, or a multiplication sign. The addition sign tells you to add two numbers. The subtraction sign tells you to subtract two numbers, and the multiplication sign tells you to multiply two numbers. The derivative sign tells you to take a derivative, right? And so it's the same idea, okay? And how we note this, we say that we're taking a derivative with respect to x. And again, that's going to be something that we talk about in other videos, right? This more, but I wanted to get that out of the way because this x, right? That's what we're taking a derivative with respect to. That's where that's going to come in, right? It's a lot, okay? But hopefully that makes sense as far as how that dy over dx comes about, okay? It's just that we use this operator that tells us that we need to take a derivative. And now that we've finished talking about that, we've talked about all the notation, the nomenclature, we've talked about what a derivative actually is. Now let's actually find some derivatives, right? I think it's about time that we get into that part of the video. So let's get into this. We're going to take a derivative of x cubed minus x. Okay, we're going to find f prime of x, right? We're going to find the slope of this function at every x value. And how we do that is we're going to plug into our limit definition of a derivative, right? Because this is what the derivative is, and to do that we need to take a limit. To find that we need to take a limit, right? And so you'll see that I switched all the x's with a's here, okay? And that's just going to make it easier to see how you're about to substitute things in, because we know what our function is, right? Our function is x cubed minus x, but now instead of having an x in there, we're going to have an a plus h, okay? And you're going to see that in a second. So let's start writing this. Our derivative is going to be f prime of a for now. We'll substitute in the x's later. But we'll start off here. This is the limit as h approaches 0 of, first off, we need an f of a plus h. Okay, and this a plus h, right, means that we're going to plug in a plus h everywhere we see an x in x cubed minus x. Okay, so we're going to write, instead of x cubed, it's going to be a plus h cubed. And instead of minus x, it's going to be minus a plus h. Okay, and then it's going to be minus a f of a, right? And so now we're just going to plug in a everywhere we see an x in this. So instead of it being a x cubed, we're going to have a cubed. And instead of it being a minus x, it's going to be a minus a. And then this is all going to be over h. Now when you're taking a derivative of just a regular polynomial, right? A regular, this is just a bunch of x's to powers being added and subtracted, right? That's what a polynomial is. Whenever we do that, our goal really is just going to be to expand this numerator, right? Because the thing is here, we can't evaluate this limit, right? I mean, if it makes you feel any better, or, think about what this limit would look like if it was x approaching 0, if you were looking at the letter x instead of the letter h, because that's what you're used to, okay? And you'll see here that, well, we have a h in the denominator that, that goes to 0. So we're going to get a 0 in the denominator if we just plug in, right? So our goal is going to be to cancel out that h, okay? And of course, you'll see here too that we get a 0 in the numerator as well. So this actually is really similar to how, in one of my other videos in this limit series, right? I talked about evaluating limits algebraically, right? That's when we had one of those indeterminate cases, right? If we got a 0 over 0 or an infinity over infinity, infinity minus infinity, all that stuff, right? So if you want to brush up on that, definitely go check out that video. right? But it's going to be the same exact thing here. Remember that with polynomials, all we have to do is just distribute out this numerator, and then we're able to cancel some h's. So let's go do that here, right? Let's keep distributing out. We'll get f prime of a as the limit as h approaches 0 of, this is something you should memorize, okay? It's something I didn't have committed to memory for a very long time, but it's something really useful because then you don't have to expand something twice. Okay, a plus h cubed is going to be a cubed plus 3a squared h plus 3ah squared plus h cubed. Okay, then we'll have a minus a minus h, right? We got to distribute that negative here. And then we're going to get a minus a cubed. We're distributing another negative, so this will be plus a. This will be all over h. Now, combine like terms, right? If we combine like terms here, we get the limit as h approaches 0. Don't forget your limit sign, right? A lot of people do that. I did that when I was in Calc 1, and it just absolutely annoyed the heck out of me, right? We can start canceling off here. The a cubed goes away with the negative a cubed. The a goes away with the negative a. And if you've done this right, everything that doesn't have an h is going to subtract off. Okay? And because that's really how any polynomial derivative is going to go with the limit definition of a derivative. Once you expand it, you're going to get, something with a bunch of h's in it, right? So we get a 3a squared h plus a 3ah squared plus h cubed minus h, right? And that's going to be over h, right? Notice here that an h's cancel off, right? We have an h canceling off here, here, here. This becomes a 2. That goes away. That goes away. And now we've canceled out that h in the denominator, and so now we can just, now we're freed up to plug in that 0 for h. But look at the aftermath. After we've canceled out all those h's, what we have left is 3a squared plus 3ah plus h squared minus 1. Right? And this is how pretty much any polynomial limit definition of a derivative problem is going to go. Okay, we're even going to do one later when we talk about second derivatives. Okay? And so what we're going to do here, we'll just plug in h equals 0, right? Because there's nothing stopping us from doing that anymore. Okay? Before, we were going to get an h in the denominator. So once we plug that in, right, we get f prime of a is going to equal 3a squared plus 3a times 0 plus 0 squared minus 1. And if you cancel out these terms, then you get 3a squared minus 1. Okay? And if we plug in a x everywhere we see an a, right, to get that f prime of x that we wanted from before, okay, because this was really just a letter swap. Okay, I just wanted to make it easier for you to see that you're plugging in an a plus h, right? For anywhere you see an x. And so if we switch out, we get a 3x squared minus 1 instead of a 3a squared minus 1. This right here is your derivative. Okay? Now remember what this thing does, right? This function that we've just found is giving us a slope of that original function that we had, the x cubed minus x, right? It gives us the slope of that function at every single x value. At every single point on that graph, we're going to know the slope because, of this function. Okay? So that's polynomials. That's the easier case. Now we're going to talk about radicals, which I think is like the second easiest, and then fractions is probably the most annoying. It's not like difficult, it's just like stupid. It's just annoying. Anyway, so radicals is up next. Now, with a radicals problem, like if we want to find the derivative of square root of x, right? This is when conjugates come in again. And if you remember evaluating limits algebraically, right? This is going to be the exact same thing as when we dealt with radicals there, right? Here we're going to do, again, f prime of a, right? The limit as h approaches 0. Okay, we want to do a f of a plus h first, so we're going to plug in a plus h everywhere we see an x. And so instead of rad x, this is going to be rad a plus h. Then we have a minus f of a, so now we're going to have an a plugged in everywhere we see an x. So instead of rad x, it's rad a. And then we're over h. Okay? Now, problem. We're going to get a 0 in the denominator, and we would get a 0 in the numerator too. As you could see, if you plugged in h equals 0, you get a rad a minus rad a, right? But there's nothing we can do at this point, right? You're looking at this and like, okay, I have everything trapped in radicals here. So to free things up from being trapped in those radicals, that's why we multiply by a conjugate here. And what a conjugate is, right, is when we multiply by this radical and we switch the sign here. Okay, and what that allows us to do is cancel out all the cross terms, and so we actually won't get any radicals in the numerator after this. You'll see that that happens. Since I'm lazy, I'm going to duplicate this down, right? Because we need to multiply by 1 here, so we multiply by the same thing on top and bottom. Okay, and so when we do that, we get f prime of a is limit as h approaches 0, right? Of we get a plus h square rooted times another square root of a plus h. That is going to make the square roots go away, and that gives us a plus h. Then we have a minus square root of a times the positive square root of a. And that's going to give you, the square roots go away, you get a minus a. And then in the denominator, you're going to have a h. Don't distribute that h through, okay? Times a plus h. A plus h plus the square root of a. Okay. Now, one thing that I used to mess up with when I was in Calc 1, okay, is I would like to distribute things through like we do with, polynomials, right? With the green section, that's exactly what we were doing. Don't do that here with radicals, because this is 0, right? That's essentially what that is. And if you start distributing this through, you're going to hide that 0 in a bunch of different places, okay? Here we know where the 0 is. It's in one place and we can cancel it off. It's going to be a little harder to see how we can cancel it off if we start distributing through, right? There's nothing wrong with it. It's just like, it makes it a little harder to see. It's kind of like having things trapped in radicals. Okay? And so let's just simplify as it is right now and not distribute through that h. If we do that, we get f prime of a is the limit as h approaches 0 of, well, the a's go away, and we get h over h times the square root of a plus h plus the square root of a. And now you can see that the h's cancel. And that's always going to happen when you have radicals, right? That's what you're looking for. Once you multiply by those conjugates, right, you're going to get the h's to go away, right? And that's what you have to do, right? You free the numerator up at this point. There's no more radicals left in the numerator, and so you're free to move things around and cancel. Moving on here and just finishing up this problem, right? We get that the f prime of a is the limit as h approaches 0 of 1 over the square root of a plus h plus the square root of a. And now we can just plug in that h equals 0, right? It's not going to make the denominator 0 here, okay? And so we'll plug that in. We get 1 over, right? This is the square root of a plus 0 right here. So that's just the square root of a. Then we get plus the square root of a, right? That's not 1 over a, right? That's 1 over 2 rad a. Oops. Just so you don't confuse my 2's with my a's, I'm going to write my 2's like this without a loop in them. Hopefully. All right. So now we're just going to plug in an x everywhere we see an a, because we want f prime of x, not f prime of a. We get 1 over 2 rad x. Oh, yep, no, I already forgot. Okay, that doesn't even look like a good square root. Ah, there we go. And what section are we on? Are we on blue or light blue? We're on light blue, or aqua or whatever. I don't know. It's a little too blue to be an aqua. But anyways, that's that, right? That is our derivative. That's f prime of x. Okay? Now remember that we could also have written this as y prime equals 1 over 2 rad x. We could have also written this as dy dx equals 1 over 2 rad x. right? There's different ways that we could have written this. Okay, so now we have our derivative function, we have our slope function, right? So now we're going to move on to fractions, okay? And I know this video has been going on for a pretty long time now, so if you want to take a quick 5-minute break, do that, and then we're going to pound out the rest of this video. I'm estimating it's only going to take another, 15 minutes to get through everything else, maybe 20, okay? But you're probably looking at the time of this video right now and being like, oh, he's completely wrong. It's taking like much less or much more. I don't know. I'm probably wrong somehow. Anyways, this example, we're we're saying that f prime of x is the derivative of 1 minus x over 2 plus x. Okay? And given that, we're going to find f prime of 2. Okay? This is the exact same question that we've been getting in the past 2 sections. Right? Now I'm just doing it with a little bit of different notation, right? I'm saying that f prime of x is the derivative of this, right? This is our original function, and when we take the derivative of it, which we signal by writing a d over dx there, that's our derivative function, right? And so I know that the notation can get a little confusing, but just know that that's what that means, okay? And then we're going to find f prime of 2, which means that we're going to find the derivative function first, and then we're just going to plug in 2 for x. Okay? So that's really all it is. And if you're wondering, okay, well, how do we take the derivative? Like, that's what this thing says, but how do we actually take that derivative? That's what we've been doing with the limit definition of a derivative. Okay? That's how you take a derivative with limits. Okay? There's other ways to take a derivative that you'll learn later in Calc 1. Okay? So, anywho, let's get on to this example. Now, this is going to be a little bit longer. F prime of a, right, is going to equal the limit as h approaches 0 of f of a plus h, right? So now, instead of having a 1 minus x over 2 plus x, right, we're going to plug in a plus h every time we see an x. So we're going to have, instead of a 1 minus x, it'll be a 1 minus a plus h. Instead of a 2 plus x, it's going to be a 2 plus a plus h. Then we're going to have minus f of a. So every time we see a x, now we're going to put an a. So we get a 1 minus a over a 2 plus a. And now that's all going to be over h. Okay. Now, what I used to do when I solved these problems in Calc 1 is I would like leave this h in the denominator, and it's just annoying to have to write this long bar and then h again. So what I would do now is I just put the h's in the denominators here, and I'll tell you why you can do that. You can do that because think about like if you have 1 over 2 divided by 3 over 4, right? This 3, right, that's kind of where h is sitting right now, because you can think of this as h over 1, right? And you can actually put that 3 on the 2. Why can you do that? Because think about this, you do like a little state change flip. This is the same thing as 1/2 times 4/3, right? And so now you see it's the same thing as having that 2 times 3 in the denominator, right? So we can multiply that h on the denominators here, and then we can get rid of the big fraction. Okay, so that's what I was trying to get across. So let's do that. I'm going to rewrite this. And I'm going to do a little bit of simplifying. So I'm going to duplicate this. And instead of having I'm going to minus a plus h, I'm going to distribute through that negative. And that's going to give us a minus a minus h. Okay? And then instead of having, I don't need parentheses here, right? I'll just have the a plus h. And I'll have the h, I'll put that up into these denominators. Right? And it's just maybe a little less annoying to have the h there rather than as a whole nother fraction. Right? It's also conserved space. So now, what do? Well, we're going to find common denominators. That's what we do when we have fractions. Okay? And our common denominators here, well, on this side, we're going to have to multiply by a 2 plus a. And on this side, we're going to have to multiply by a 2 plus a plus h. So we get a lot of distributing going on here, but, it's going to happen. Okay, and so we're going to multiply 1 minus a minus h by the 2 plus a. And then we're going to multiply the 1 minus a by the 2 plus a plus h. Okay, and just to make sure that you realize that these are 2's, not a's. I know that can get a little bit confusing. I'm going to write those 2's like that. Okay, in the denominator, we have a 2 AH, we have a 2a. Okay, and so now we're ready to go. And by the way, yeah, I did combine this this denominator, right? Since we have the common denominators, we can write it all as one fraction. So hopefully that made sense. Okay, so we're going to distribute now. Okay, distributing here, we're going to get a 2. We'll get a minus 2a. We'll get a minus 2h. We're going to get a plus a minus a squared minus ah. Then we'll get a minus, it'll be like a negative 1 times 2. Right, so it'll be minus 2. Negative 1 times a is negative a. Negative 1 times h is negative h. And then we have a negative times a negative, that's going to be a positive a. So we get a positive a times 2 is 2a. Oops. A positive a times a is a squared. Positive a times h is ah. So running out of room here. Of course, I just have to flounder at like the last. Okay, anyways. This is going to be all over a h times 2 plus a plus h. And a 2 plus a. Now, okay, this is really the same thing as having a polynomial at this point, right? It's the same idea as the green section, right? Now we're canceling a bunch of things off, okay? And remember what happened in the green section. We're canceling a bunch of things off, like we did here, and then we're going to be able to cancel h's, and that h is going to cancel with the h in the bottom. That's the same exact thing that's about to happen here. Watch. Watch what cancels. Everything except with the things with the h's are going to cancel here. Gonna pick out the blue marker here. The 2 cancels with the negative 2. The negative 2a cancels with the positive 2a. Positive a is going to cancel with the negative a. And let's see, is there anything else here? Negative a squared with the a squared. Okay, look at what's left. Everything with the h's. Okay, and actually, it looks like we have a negative h and a positive ah, so those are going to go away too. All right, so sometimes things with h's are also going to go away. So these two terms are going to combine. We'll get a negative 3h on top. And in the denominator, that's where we're going to get the h, the 2 ah, and we'll get the 2 plus a. Okay? And so now we can cancel those h's. And we get f prime of a is the limit as h approaches 0 of negative 3 over a2 plus a plus h times a2 plus a. Okay? And now we can plug in 0 for h, right? There's nothing stopping us now, because this h being 0 does not make our whole denominator 0. So this becomes negative 3 over 2 plus a squared. Right? We get a 2 plus a here. We get a 2 plus a here. And so we square it. Okay? That's our derivative. So if we plug in x everywhere we see an a, we get negative 3 over a 2 plus x squared. Okay? Great. Now that's not what the problem asked for, though. The problem asked us to plug in a 2 for x. That's what f prime of 2 means. So that's what we're going to find. We're going to plug in a 2. And when we do that, we get a negative 3 over a 2 plus 2 squared. And that gives us a 4 squared, that's 16. We get a negative 3 over 16. Okay? That is the answer to this problem. Okay? So really, when we have fractions, we find common denominators. Okay? That's really what we do. When we have radicals, we use the conjugates. When we have polynomials, we just expand and cancel, just like we do at the end of the fraction problem. So now I'm going to talk about second derivatives, and that's really going to be the last thing that we talk about in this video. Okay, now I mentioned before in this video that the slope of a position time graph is the velocity, right? It's how fast you're going. But also, let's talk about a velocity time graph, right? This is, velocity is already the derivative of position, and so if you want to write it as, maybe x prime instead, right? So I can say v or x prime, right? This is now a graph of the derivative, right? What's the slope of this represent? Well, let's think about it. Slope is rise over run, right? And since the rise, right, the rise is how fast you're going, right? That's the y in this case is going to be measured in meters per second, right? And the x in this case, which is actually t, okay, is going to be, well, how long it's taking you to do that. So that's measured in seconds. Now, if this is kind of like the h thing from before, right? This can go right here. And so this slope is measured in meters per second squared. Okay? That, my friends, is called acceleration. Right? Acceleration is how fast your velocity is changing, right? So, the derivative of a position time graph is velocity. It's how fast your position is changing, and how fast your velocity is changing. The slope of a velocity time graph is your acceleration, right? And so second derivatives are useful in the real world, okay? So now we're going to actually find some second derivatives, right? The notation for a second derivative. I'm going to get into a little more notation, then we're just going to find a quick second derivative, and that'll be it for this video, okay? To signal that we want to take a derivative, we put a d over dx out in front. We talked about that earlier in this video, okay? So, for example, if we have y equals 2x, we say that we want to take a derivative, which we've been doing by using that limit definition of a derivative, right? And we put a d over dx out in front on both sides. When we do that, we get a dy over dx, right? We just kind of multiply that y onto the d over dx. And that's going to equal, well, what's the derivative of 2x? You should be able to tell me, right? Well, the slope of 2x, that's what the derivative is. The slope of 2x, that's a line, it's just going to be 2. Okay? But, well, now we want to take a second derivative. And so what we do is we don't just have one d over dx out front, we actually have two. So it's going to be d over dx of d over dx of y. Right? And then a d over dx of d over dx of 2x. Right? So there's two d over dx's here. There's two derivatives that we're taking. And so, well, how do you write that? You write that as, well, it's like a d over dx squared on your y, right? And then over here, it's like a d over dx squared on your 2x. Oops. Okay? And I want a little more room to write that. Okay? And so what we can do is we can write that as d squared over dx squared on y equals d squared over dx squared on 2x, right? Like I know this is a bunch of different variable stuff here, but realize, we know what these variables mean. I've talked about that. And now we're just, applying some exponents to them, okay? And, when we finish this up, right, we just put the y on like usual, like we did in the example above. And that's how, a lot of people wonder why the second derivative is written this way. Well, hopefully this example clears it up, right? It's literally a d squared dx squared acting on y. And this is equal to a double derivative of 2x. So we have to take two derivatives. Well, let's think about it, right? If, we should know what that double derivative is going to be. dy over dx is 2, right? That's the slope of y equals 2x. But what's the slope of y equals 2, right? That's the derivative. So the derivative of the derivative, right, the slope of y equals 2, right, y equals 2 is just a straight line. Its slope is 0. And so actually, in this case, this would be 0, right? And so hopefully that makes sense, right? Because that derivative of that is what this is meaning, right? It's the double derivative of 2x. And so, yeah, that just ends up being 0, okay? Now, listen, you don't have to understand everything I'm talking about with second derivatives yet, because you're going to be spending a lot of time with them, for probably a solid span of like a couple weeks, okay? So it's, you're going to be fine if you don't get it already. No big deal. Most people don't get it already. Okay, so if you do, you're ahead of the curve. Now, as an example here, find the second derivative of f of x equals x cubed minus x. Okay, we already found in the first example when we were dealing with polynomials, right, that this was the first derivative, right? That's the first time we take a derivative, that's what we get. And so what we do now is we take another derivative of this. And so if this is f prime of x, we're going to modify our limit definition equation a little bit. And so we're going to take another derivative. And so really it's going to be f double prime. That's how we denote the second derivative, right? And so I guess, in the notation, you could also write f double prime of x, and you could also write y double prime. Okay, but that was the notation with the d's and stuff. Okay, mostly you'll probably see it like this. But yeah, so but it doesn't make everything that we did before useless, by the way. F double prime of a is going to equal the limit as h approaches 0 of, instead of f of a plus h, is going to be f prime of a plus h, right? It's going to be this stuff getting plugged in. It's going to be minus f prime of a, and then it's going to be over a plus h. Not a plus h, sorry, just h. Okay? So now let's start plugging in. This is going to be a really quick one. This will be the quickest derivative that we take all day. We start plugging in here. F prime of a plus h, right? We're going to plug in a plus h everywhere we see an x in the derivative. Okay? Instead of a 3x squared minus 1, it's going to be a 3a plus h squared minus 1. And instead of a 3x squared minus 1, when we plug in a, it's going to be a 3a squared minus 1. And then we're over h. Okay, so let's do a little bit of distributing. That's what we do with polynomials, right? We distribute everything out, and then we're going to be able to cancel some h's and, combine like terms, and that's really going to be it, right? That's how polynomial derivatives are going to work every time. Distributing out here, you should also memorize what this is when you expand it, right? That should be the first thing you memorize. This is going to be a squared plus 2ah plus h squared minus 1 minus a 3a squared plus 1, right? Because you have to distribute that negative. And this is going to be over h. Now we can do a little bit of canceling already. We see the negative 1 and the plus 1 go away. But still going here, we can distribute it through that 3, and so we get 3a squared plus 6ah plus 3h squared minus a 3a squared all over h. And would you look at that? The 3a squareds cancel off, and so all we're left with is things with h's. That's exactly what happens with this, right? That's what's always going to happen. We're going to get rid of those a's, or the h's. Right? We get rid of the h's right here. This becomes just a regular h, and then that goes away. So this becomes 6a plus 3h. Now notice what happens here. We can plug in a h equals 0, right? We can plug that in, so we get 6a plus 3 times 0. And that's just 6a. Right? Again, we can just plug in that h equals 0 because, well, there's nothing stopping us from doing it. Before, there was a 0 in the denominator when we did that, and so, now we can actually plug that in because there's not a 0 in the denominator anymore. Anyways, if we just plug in that x back for a, just like we usually do, right, we get that the second derivative of your f, right, is going to be 6x. And so that's our answer there. Oops, that looks kind of gross, so I'm going to do that again. All right. So hopefully that makes sense. That's the idea with second derivatives. Okay, we just really are just taking another derivative of the derivative. So let's just wrap up this video with some review. I want to make sure that you understand everything that we talked about in this video, right? So there's three main cases when you have a limit definition of a derivative, right? A lot of people, they see a limit definition of a derivative problem and they go nuts, okay? That's what I used to do. That's what a lot of kids in my class used to do. And so, there's really three main things that happen. It's either you have a polynomial like x cubed minus x, you have a radical. We did our example in the light blue section. That was just rad x. Or you have a fraction. We did that example in the dark blue section. Okay? Now, when you have a polynomial, all you're doing is you're just distributing out and you're canceling your h's. Right? That's what we did. And we just did that again with the second derivative example. With radicals, you're multiplying by conjugates. Okay? And you can review that from earlier in the video. Right? You multiply by that conjugate on top and bottom. What that allows you to do, right, is once you multiply by those conjugates, you free up that numerator, right? Once you have that numerator freed up, now you're able to cancel some h's, okay? And so that's how we handle radicals. Now, there's also fractions, and for that we find common denominators, and then really once we have common denominators, it really just becomes a polynomial problem from there. Okay, fractions can be really annoying because finding common denominators can result in like a lot of distributing, but really that's how you have to solve the problem, okay? I do have three last tips for this video, and that is, don't distribute through that h in the denominator, right? Our goal is to cancel those h's, and so it just becomes a lot clearer to cancel that h if you don't distribute it through, okay? We found that out with the example, right? Well, right here, we didn't distribute this h through in the fraction example, right? And in the radical example, again, I told you not to distribute through that h because then it'll become more clear that the h's cancel, right? Our goal is to always cancel the h. Cancel the h. Okay? Always keep track of that derivative notation too, right? The first derivative, you can write that as y prime f prime of x or dy over dx, right? We see it written this way, but it can also be written this way, and on occasions it's written that way as well. Second derivative notation, we call that, y double prime f double prime of x and d2y over dx squared, right? d squared y over dx squared. And the last example, or the last thing I will mention to you, is do not forget to include your limits. Okay, this is easy points off on a test. Some professors will, or teachers, whatever, they will just go off and everywhere they don't see a limit sign, right? If they don't see these written here, they're just going to start marking things off, right? They're going to be like, nope, sorry. And they'll just, every time they don't see the limit, they'll go -1. And that's so annoying. But anyways, that is going to do it for this video. Now, do remember that I have that full Calculus 1 course in the description down below. Again, that's just a better chance for me to help you one-on-one, and I have loads of practice problems on that for you to go through, and so you are able to better retain what we talked about in this video. Okay? So, again, I hope this video helped, and I'll see you soon.